So where did we stop? We talked about the Eisenstein series. So it's a sum over lambda in the lattice being the lattice generated by 1 and tau. Tau is in the upper half plane of 1 over z plus lambda to the power k. And we proved that if you take for all, let's say, gamma A, B, C, D in gamma equal to SL2Z, if you take EK of gamma tau, that is EK of A tau plus B over C tau plus D, this comes out to exactly C tau plus D to the K times E. And this property, this key property, is what we call a modular form. Modular form of weight K. Of weight K. This being the K. Okay. So this means that it's basically enough to know EK on a fundamental domain, whatever that is, for the action of SL2Z. So let's talk about fundamental domains for a second. Fundamental domains. So we've used this word, but I don't know that we've actually defined what a fundamental domain should mean. It's like a fundamental tile, right? A tile which moves around. So like if our group was Z and our discrete group Z is a subgroup of the continuous group G. So what's a fundamental? So let's say D is fundamental domain for gamma acting on G. How do the integers act on the reals? Here's the real line. Here's G, the real line. And the integers, of course, translate by 1 or by 20, right? So up to integer translation. So D, what's a fundamental domain? Well, domain, okay, different people have different definitions. For me, domain is an open set. So can you think of a fundamental domain for this action? Any unit segment, like minus a half, or 0, 1, something like this, right? What are the salient features of the domain? I would say that how should we put this? If Z and W are both in the domain, and Z is equal to W, well, this action is additive, so it's W plus an integer, then in fact, Z equals W, and that integer is the identity element in the group. So that's one condition. So that's the fact that this tile has at most one representative. If I have 2 points Z and W, if Z and W are both elements of the same domain, and I'm calling this a fundamental domain, then if they differ by an element of gamma, that element should be 0, and they should be the same point. Right? So it's sort of so this is the uniqueness, unique representability. And then representability, well, okay, knowing that the orbits, knowing that the translates of D by integers are disjoint, right? These are all disjoint. So if I take their disjoint union, so I take, let's say 0, 1, and 1 to 2, and 2 to 3, and 3 to 4, and so on. Well, I might be missing some points because I said this was open, and these will be disjoint. But if I close it up, if I take the closure of that should get me all of G, namely R. Okay, so this is the covering. So a fundamental domain is like a unique covering. You have a tile, so D is a kind of tile that uniquely covers all of space. It's a tile, so there's no overlap. The tiles don't overlap as you move them around by the group, but they do cover the whole group, at least in the sense of closed. There's all kinds of different choices you could have made in making this definition that would all be equivalent. Maybe they maybe they're closure tiles, but this happens on a set of measure 0. You know, you can not worry about the boundary or worry about the boundary. You can say they include 0, but not 1 if you want an exact tile. People make all kinds of different choices. This choice is good enough for us. Okay, so this is a kind of reduction algorithm. This is really reduction algorithm. It's a reduction algorithm because what do I mean by this? If I give you, so given any z in R, the reduction algorithm returns this reduction algorithm returns sort of the simplest representative for the coset z plus the group, the discrete group. Right? If I give you here's the real line, and I give you a number 40.179 yada yada, so this is z, then there's an entire coset. This is z plus z, of course. Gamma is z in this example. So this is all the integer translates. So gamma plus z plus gamma is all the integer translates. And then what's the algorithm? Let's say this is our fundamental domain. What's the algorithm for finding the simplest representative, meaning the one? So there's an element in here, let's call it z naught, that will be in our, at least for almost all, okay, so there's some that'll be missing, but at least for almost all z, there's some z naught that's actually in the domain. Okay.
You said some that are missing? Does it mean if you have one missing, you're missing all of them because they're all?
That's right. That's right. So the integers, if I use 0, 1 as the open domain, then all the integers are missing.
Oh, no.
All the integers, there will not be.
I understood.
Yeah.
You don't do integer intervals. What were you saying about missing 1 point?
Oh, missing measure 0 set of points.
Oh.
Except for yeah. For all but a measure 0 set of points, or let's make it all points, you can get into the closure of the domain. Okay, maybe not uniquely. Right? Because you could, once I put the closure, now I have 0, 1, including 0 and 1. So whether I move to 1 or 0, there's some choice being made there. Okay, but what's the reduction algorithm? Well, this group Z contains the map that sends Z to, so inside Z, and I'm thinking of Z not as the integers, but as the action, the group acting on the reals. It's a subtle difference, right? It's translation by 1. So if I call this element, let's say T for translation, the algorithm is, well, if I'm bigger than 1, then I use T inverse. And if I'm less than 0, then I use T. So what's the algorithm? If Z is greater than 1, apply T inverse. And if Z is less than 0, then apply T. And repeat. And eventually, you'll wind up inside 0, 1. I'm doing something completely trivial. Repeat until you halt. Repeat until you halt. And you halt when neither of these conditions applies. In other words, Z is at least in the closure of D. Does that make sense? So this is completely and utterly trivial, but it's about to be non-trivial. That's why I'm spending so much time on it in this trivial case, so that we see what to do. Okay, let's do a slightly less trivial setting. Is let's say we have W1 and W2 acting on translation by W1 and translation by W2 acting on R2. What's our reduction algorithm? So here's W1, here's W2. Here's R2. Here's a random point Z in R2. What's the reduction algorithm? Exactly. So the domain, we've already discussed this. The domain is this parallelogram. How do I get the parallelogram? Well, think about these parallel lines gotten by translation by W1. And there's more of them here. And think about these parallel lines gotten by translation of the line through W1 by W2. Okay, so this is the domain D. D is that fundamental parallelogram, that tile, the open tile. And then what can I do? Well, if I'm not inside this cylinder, let's see, can I color this? If I'm not inside this cylinder, what's the algorithm? This is like a reduction algorithm, you could say. It makes the reduced Z is the image that's inside the fundamental parallelogram. So the reduction algorithm, and it's now not just points that are missing, there's entire line segments that are missing if we're taking the open disk. Okay. The reduction algorithm is if outside this parallelogram, what should I apply?
In a W1, W2 basis?
Sure. What do you mean?
Oh.
G is just a pair of real numbers.
Yeah. If that's like a vector in a W2 basis, then you can like take floor value of the W1.
That's right. That's right. You can do exactly that. This is a that's a little too slick because there's no such thing in what we're about to do. There's no nice basis expansion. But what's equivalent to that? I mean, this is like the same thing here, right? You're just taking the floor function. So what point did I take? 40.197. Of course, the point is going to be 0.179 dyslexia. So of course, I'm taking the floor function, right? Or the opposite. I'm subtracting off the floor. It's the floor function. It would be 40. I'm subtracting off the floor, and I'm just taking the fractional part. Whatever, same thing. So yeah, but what's the equivalent thing to that? I called it translation by T up and down. Here we would translate by W1, yeah, by plus or minus W1 until inside this rectangle, until inside. And then, so this is step one. And step two, well, okay, good. We've translated by W1. So I translate by W1 there, I translate by W1 there, and now I'm inside that cylinder. And now what? Yeah, and I have another fundamental parallelogram, fundamental cylinder corresponding to translation by W2. And if outside this cylinder, what color was that? That, I think. If outside that cylinder, apply plus or minus W2. And well, I am outside that cylinder, so I'm going to apply W2, I guess minus W2, minus W2, minus W2, minus W2, and oh, bingo, there's my equivalent point. Why did this work? How come when I apply W2, it doesn't ruin the fact that I was already inside the green cylinder? You see the way I drew it, I never left the green cylinder once I got inside. Is that obvious? It is, but there's one word we have to add. This group action is well, it's not transitive on all of R2. Transitive would mean that it can take any point of R2 to any other point of R2. But it's something much simpler. If I do W1 first and then W2, does that make a difference? If I translate, it's commutative. It's abelian. Yeah, exactly. It's abelian. It's abelian, so the reduction algorithm is just trivial. You simplify with respect to W1 as best you can, you simplify with respect to W2 as best you can, and you're done. Okay, so now let's think about, so our case at hand, again, what's the at hand? It's that we're trying to understand, this says it's enough to understand any modular form of weight K on, if we had a fundamental region for the action of SL2Z on the upper half plane. We could just worry about the values of the Eisenstein series on that fundamental region. So what is it? Let's work it out. The case at hand, gamma is SL2Z acting by multiplication, which is non-abelian. Non-abelian. And it acts on the space. G didn't have to be a group. It acts on the space. The upper half space is, well, it's not a group because it's not a group. So what's the action? Fractional linear transformations. Okay, so if you give me, so here's the upper half plane, you give me some random point Z in the upper half plane, how do I reduce it as much as possible? We want a reduction algorithm to a fundamental domain D for the action of gamma on H. How can I make it simpler?
Domain that strip.
So one element, let me get to exactly that. One element in SL2Z, I claim the matrix 1, 1, 0, 1 is in SL2Z. Well, that's just obvious. It's integer entries, the determinant is 1. And how does it act? 1, 1, 0, 1 takes Z to 1 times Z plus 1 over 0 times Z plus 1, 1, 1, 0, 1, also known as Z plus 1. This is T. This is translation. So I can definitely take whatever this point is and translate it by 1, T inverse in this case, until I get, let's say, between minus a half in the real part. Okay, so I can translate it over to minus a half. Is that it? Is that the best we can do? There's much more to the group SL2Z than just this Z subgroup. We found 1Z01 is a subgroup of SL2Z. So that's one element. It turns out there's another element, and that other element we can write as this. This is another interesting, if you just tried to find the simplest elements of SL2Z you could, using like zeros and ones. The next one that you would stumble on is this one. It's traditionally called S. The determinant of this is 0 times 0 minus 1 times negative 1. So this is an SL2Z. And what does it do? 1, 0 to Z. Negative 1 over Z. Okay. Why is this? I don't know that we did this calculation. If I have any element of, if I have any matrix A, B, C, D acting on Z. So again, this is AZ plus B over CZ plus D. Let's say this is real. So this is in 2 by 2 real matrix. Question? No. What's the imaginary part of this? Let's work this out. It's not that hard. So the imaginary part, if I just look at this fraction again, AZ plus B over CZ plus D, well, Z can be complex, but A, B, C, D are real. And so if I want to access anything about this, I should multiply the top and bottom. Exactly. C, Z bar plus D. C, Z bar plus D. Okay, so if I want to work out the imaginary part of this, That's not too bad. It's the imaginary part of, the denominator is now real. It's just norm CZ plus D squared, because I multiplied whatever this complex number is by its conjugate. How about on top, I have an AC ZZ bar, so that's an AC Z squared. I have a B times D. I have an A times DZ, ADZ, and one more thing is a BCZ bar, BCZ bar. So let's try to understand the imaginary part. Okay, so there's this real denominator, so that's already there. So I just have to work out the imaginary part of the numerator. And this is real, so that imaginary part is 0. B times D is real. That imaginary part is 0. The imaginary part of ADZ is ADY, if Z is X plus IY. And BCZ bar, the imaginary part is plus BC times negative Y. So this is AD minus BC times the imaginary part of the original Z divided by norm CZ plus D squared. Sorry, that's a B. You don't like my B? I don't like my B either. Is that any better? Or I just make it just as bad as before? Okay. So this is, of course, the determinant of your matrix. The determinant of, let's call this matrix G. So if the determinant is positive, if, I mentioned this last time, but I didn't do the calculation. If the determinant is positive, then the imaginary part of GZ and the imaginary part of Z is positive, then the imaginary part of GZ is also positive. Okay, we should have checked that actually SL2Z does send things with determinant, things in the upper half plane to the upper half plane, and it does because all of the determinants are in fact 1. Not only are they positive, but they're 1. So for gamma in SL2, in fact, R, not even Z, the imaginary part of gamma Z is equal to 1 times the imaginary part of Z divided by this factor, this cocycle, CZ plus D squared. There.
Does PSL2Z have less generators than SL2Z?
That is an excellent question. We're going to get to PSL2 in just a second. We're going to need PSL to say some of the things we're saying. I'm trying not to confuse things further by introducing the projective group, but indeed, T and S will also generate the projective group. In PSL, this element has order 2, whereas in SL2Z, it has order 4. So if I multiply S by S, let me just make this quick. Let me not think about that. Think about that fact. So I claim, let me put this little claim. S squared is -1 in SL2Z. But of course, -1 is 1 in PSL2Z, where PSL is you identify things with their negatives. S squared is 1 in PSL2. Okay. So they're different groups. PSL2Z and SL2Z are different groups, but they have the same generators. And in fact, the action doesn't care about multiplication by -1. Okay, let me not go there. Let's think about what this is doing geometrically. So what is S doing geometrically? So SZ again is -1 over Z. And what's the imaginary part of SZ? Well, again, we can work it out from here, but we have a nice formula that tells us what the imaginary part of SZ will be. It's the imaginary part of Z divided by what is CZ plus D for S. It's just Z. Yeah, C is 1, D is 0. It's just Z squared. Okay, so here's an observation. If the absolute value of Z is strictly less than 1, then we're dividing here by a number less than 1, then the imaginary part of SZ is strictly larger than the imaginary part of Z itself. And that suggests an algorithm. The algorithm it suggests is the following. So you start with your arbitrary Z. So here's my algorithm. I'm going to simplify Z with respect to the element T. So use T or T inverse until the real part of Z is less than a half. I can't say less than, strictly less than, because, well, that might not be possible, right? If the real part of Z is exactly equal to a half. So I'll use T until I get inside of here. Now, if Z in absolute value is less than 1, so where is that? Here's 1, here's -1, so here's the unit circle. If I wind up inside this unit circle, I'm going to apply, so this is step 1. Step 2, if inside the unit circle, when I apply, I'll apply S. Now, what does S actually do geometrically? Let me leave it as an exercise for you, that what S actually does geometrically is it moves Z across 1. It inverts geometrically. S inverts in the circle, in the unit circle. Eric, you want to say something? Want to ask something?
It reflects over the Y.
And reflects over the Y-axis. And reflects across Y-axis. Do you guys all know what I mean by inverting in the circle? No, great. So inversion in a circle is, circle inversion is this. The Greeks love this. Well, one can argue about whether the Greeks loved this or not. I claim they loved it, and some historians I respect say, no, they knew nothing about inversion. But so if you have a point, let's call this point P, then inversion in a circle is a point P prime. So this is P, this is O. This is a point P prime with the property that if P is 2/3 of the radius, the distance OP is 2/3 of the radius of the circle, then the distance OP prime will be 3/2 the radius of the circle. In other words, it's inversion. It's just the map x goes to 1 over x, but linearly in that direction. In other words, if the ratio OP to R should be inverted to the ratio of OP prime. In other words, R over OP prime. So this is closely related to the notion of quadrature. It's the fact that OP times OP prime is equal to R squared. So if you had some fun geometry, elementary geometry, and you know that, things about, okay, anyway, let's not do elementary geometry. There's a there's a whole lot of beautiful stuff there that we're going to ignore. So inversion in the unit circle. So what I've drawn here is this point, which, I don't know, 3/4 of the distance to O. So inversion will take us over here to a point 4/3 the distance to O. And then I'll invert across the Y-axis, which is just a mirror inversion. So I wind up here. Okay, so if this is Z, then over here is SZ. And so we're done. Once we simplify things with respect to T, and then we simplify things with respect to S, we're done. Eric.
I was going to ask, why put it outside the active state?
We might not be done. We may have ruined what we did in step 1 because the group is not abelian. Unlike translation by W1 and then translation by W2 that we could do in other order, once we got things working for W1, we just applied W2, and then we got things working for W2, and then we're done. Because the group was abelian.
We've done the other one first.
We could have done the other one first, but then we'd still ruin, once I start moving by T, I can change whether or not I'm inside or outside the unit circle. these two don't fix one another. So we might have to do it again. And then apply 1 and apply 2. Oh, if we're not inside the unit circle, we can just stop. Else, halt. So if we're outside the unit circle, but inside this minus a half, as we got with step 1, I claim halt. So if we wind up somewhere here, we should stop. And my claim is the algorithm always halts. My claim is that the algorithm halts. This reduction algorithm halts. And in fact, what it which implies that the region D, okay, it doesn't exactly imply. There's a little bit more to say, but it turns out that the region D, which is a set of all points in the upper half plane with real part of Z strictly less than a half, since we want to take an open region, and absolute value of Z strictly greater than 1. So we're outside the unit circle. We're inside minus a half. My claim is that this thing is a fundamental domain, a fundamental tile for SL2Z. So as you move this by SL2Z, you fill up the entire upper half plane, at least when you use the closure instead of the region itself. And two elements inside this domain that differ by an element of gamma are actually the same point, and the element that they differ by is the identity, which would not be true in SL2Z, because -1 doesn't do anything. -1 is not the identity element, but it is true in PSL2Z. So that's where we have to go to PSL to make that statement correct. But let's get to all of that. Does any of this make sense? Have I lost you? Eric.
So you said two elements differ by what? And there's two.
Yeah. So our claim or our definition by example of what a fundamental domain should satisfy is, first, the representation of any element should be unique. In other words, if I have two elements in the fundamental domain that differ by the group action, the discrete group action, which will now be a multiplicative action instead of an additive action, then those two elements should be the same, and the matrix and the group action that does it should be the identity. So that's the uniqueness property of it, that the tiles don't overlap. You don't want your bathroom floor, the tiles are stacked on top of each other. You want them to be separate, but you also don't want them to have any gaps. So you want them to cover everything. They want it. So this is the disjointness of the tiles, and then the covering of the tiles. An exact covering, disjoint covering. And maybe disjoint is a better word here. That's exactly what I'm using here. Okay. So first, let me prove the covering. In fact, in the interest of time, maybe that's all I'll prove. Why does the algorithm halt? Why can I get any element of the upper half plane, any point in the upper half plane, I claim, after doing this operation more and more times, will eventually wind up in this region? Any thoughts, Eric?
I think after at least one cycle of the S&T, you should be able to get the imaginary part big enough.
That's big enough for what?
Oh, to be greater than.
By the way, what is this imaginary part? The real part's a half. The length is 1. So that height is. You're almost on the right track. That height is √3/2. Hopefully you guys remember your 30, 60, 90 triangles. So just talking about imaginary parts isn't enough. If the imaginary part is bigger than 1, then sure, I'm good to go. But the imaginary part being bigger than √3/2, there's still a big, there's still some shape here that where we're not outside the unit circle.
So certainly, if you do this procedure over and over again, your y part is increased.
Yes, exactly. As we apply S, the y part is strictly increasing. So imagine that this doesn't halt. We have some initial point Z0, and I'm going to draw the height of that. This is the imaginary part of Z0. So when we apply t, we wind up inside this region. Then we apply s, we wind up with a larger imaginary part. Then we apply t again. Then we apply s. Then we apply t with an even larger imaginary part. Then we apply s with an even larger. So we get this sequence. So if not, there exists an infinite sequence, Z1, Z2, Z3, and so on. And each of these is, of course, gamma 1 times the base point Z0, and then gamma 2 times Z0, right? Just gamma is a matrix in SL2Z gotten by multiplying all the T's and the S's and the T's and the S's together. We get this sequence, and this sequence is contained inside the region where the real part of Z is at most 1/2, and the norm of Z is at most 1, and the imaginary part of Z is at least the imaginary part of Z0, some fixed number. And the imaginary part of Z is at least some Z0. But this is a compact region. And so if I have an infinite sequence of points here, well, I can't be drawing them down. They have to constantly be going up. If they're constantly going up, it doesn't matter whether they're constantly going up. So there exists a subsequence that's convergent. Okay, so there's some subsequence of these guys that converges. But let's think about this property. So the imaginary part of gamma Z is always at least some Z0. Gamma Z0, right? We have some gamma is a sequence. I don't want to say gamma. Okay, let's say gamma J. So the jth element acts on Z0, the original point that you started with, and its imaginary part is at least Z0 because we keep winding up inside this set. It is strictly increasing. I'm being crude. I'm being even cruder than the strict increasing. But what is this? Again, if gamma J is A, B, C, D, I guess A, J, B, J, C, J, D, J, the imaginary part, we remember what this was? This was, sorry, this is not, what am I saying here? Z0 is a complex number. It's the imaginary part of Z0. The height of Z0. Imaginary part of Z0. Okay, so what's the imaginary part of gamma J Z0? You remember? All I'm saying is, so when I move Z0 into this point, that's applying a bunch of T's. Then I apply an S. So let's keep track of all of those. That's a bunch of T's and then an S. That's gamma, well, a bunch of T's is gamma 1. And then the S and a bunch more T's is gamma 2. And then an S and a bunch more T's is gamma 3. So each of these gammas, each gamma J looks like a bunch of T's and then an S, and then I guess I'm applying them in the other order. It's a bunch of T's and then an S, and then a bunch more T's and then an S, and so on. Okay, does that make sense? And I keep winding up in this region. What is the imaginary part of gamma Z? We worked out this calculation a minute ago. Anybody remember what it is? Yeah, exactly. So it's the imaginary part of Z0 divided by norm C, I'll call it Cj Z0 plus DJ squared. Is at least the imaginary part of Z0. Let's multiply this to that side and divide by imaginary part of Z0. That means that Cj Z0 plus DJ squared is at most 1. But what is this? If Z0 is x plus Iy, this thing is equal to Cjx plus DJ squared. I guess I should call it x0 because it comes from Z0 plus Cj y0 squared. For x and y, for x0, y0 fixed, what is the region if I draw in the CJ DJ plane? This is kind of horrible notation. What is this region? What is this function? The C and the D are the variables, and I want to know the region where x and y are fixed. What's the region where this this squared plus that squared is less than 1? It's just some ellipse. It's just some weird ellipse. How many integer points can this ellipse have? Finitely many. So there can only be, so this thing, this infinite sequence has only finitely many possible bottom rows. So there are finitely many CJ, DJ in Z2 in this ellipse, satisfying this condition. Okay. Well, fine. Well, so the bottom rows can only have finitely many elements, but maybe the top rows can do all kinds of crazy things. My claim is that if gamma 1 and gamma 2 have same bottom row, they differ by t's, by translations. Why is that? This is very easy to see. If gamma 1 is equal to A, B, C, D, and gamma 2 is equal to, let's say, alpha, beta, same C, same D, so they have the same bottom row. Let's compute, I don't know, gamma 1, gamma 2 inverse. So what is gamma 1, gamma 2 inverse? Gamma 1 is A, B, C, D. Gamma 2 inverse, I'll flip the diagonal, D alpha, negate the off diagonal, negative beta C. Thank you, negative C. That's crucial right now. So what will be the bottom left entry? CD minus CD. It's going to be 0. These are integer matrices. The determinant is 1. So this is either 1, 1 or minus 1, minus 1. In PSL2, that's the same thing. And then whatever is here is some integer. So it's just powers of t in PSL2. Okay, so these matrices, in fact, can only have finitely many C's and D's. And the numerators differ by translation, but you can't do any translation if you're inside this minus a half. So this has to be a finite sequence. We get a contradiction. Unless you wind up on the boundary. Yeah, so anyway. So, so algorithm halts. And what's that? Here's a much slicker proof. The way that I would say this is the group gamma is discrete. I can't have, it's integer, right? It's integers. And if I had infinitely many points here in this compact region, that it would have a limit point. And there's no limit points here. It's a very long-winded way of saying can't have limit points of a discrete action, unless you're going to the boundary. You can have limit points going down to the boundary, but this is in the interior of the group action. Okay. I did want to get to lots of other stuff. So algorithm halts, let me skip the fact that we've proved that it tiles. We haven't proved that it's unique, that they're disjoint. I'll leave that to you. But this is the reduction algorithm. This most of the time attributed to Gauss, although I think Legendre deserves more credit than he's often given, and by me. Okay, so what that means is if we know the value of EK on just this domain, it's not that it's the same everywhere else, but it changes everywhere else by this process. And if we know ek of tau for tau in this domain, then we know it everywhere. Then we can extend everywhere by modularity. By the way, what does modularity say for the two elements that we've been talking about? Translation, we'll get CZ plus D to the K times EK of tau. What is CZ plus D? What's the translation matrix? 1, 1, 0, 1. So CZ plus D is down here. It's just 1. Okay, and how about the other one? EK of -1 over tau. What's the factor? CZ plus D is now tau plus nothing. So it's tau to the K. CZ plus D. Okay, so this and so these two relations generate all possible relations. If you know these two things, then you know everything about this EK. All right. Good. Let's use that idea to try to solve. I don't think I'll get to the 4 squares, but we can do the 2 squares. Sum of 2 squares here. So let me remind you, this is like 16, I'm going to make up a number, 1630s. Fermat shows that primes that are 1 mod 4 can be expressed as a sum of 2 squares. Primes that are 3 mod 4 cannot. And 2 is a sum of 1 plus 1. I'll say 1770s, Lagrange's 4 square theorem, Lagrange, shows that actually any integer for all n, positive, n is a sum of 4 squares. These were done by sort of bare hands elementary means, but now we can understand these proofs in fancier terms that give us more information, actually. So starting with Jacobi, Jacobi started investigating things that he called theta functions. So here's his theta function. The Jacobi theta function is this function. Theta of, I'll call it tau, is a sum over n in z, e to the pi I n squared tau. Why would you look at such a thing if you're interested in solving equations in naturals or primes? Well, what is theta squared? Okay, so I'll just multiply theta by itself. So let's use x for the first variable and y for the second variable. So this is a double sum. Maybe I'm doing too much at once. E to the pi I x squared plus y squared tau. You buy that? And so if I put this into a single series, so there's an e to the pi I n tau. I want to know what the coefficient in front of e to the pi I n tau is. The only n that will arise will be sums of 2 squares, and they'll all be positive. And how many times this number occurs, this power of e to the pi I tau occurs, is exactly the number of representations. So let's call this R2 of n. R2 of n, where R2 of n is the number of ways that n can be written as a sum of 2 squares in the integers. Does that make sense? Everybody see that? Eric?
Everything else will cancel.
There is nothing else. So anytime you get, this is like we're adding up all the possible contributions. Like, how do I get an e to the pi I times 5 tau? Where's that? How many times will e to the pi I 5 tau occur? It'll occur when x is 2 and y is 1, or when x is 1 and y is 2, or when x is -1 and y is, so there's a factor of 4 there for pluses and minuses. That's the only way that I'll get an e to the pi I 5 tau. And that's exactly what this R2 is recording. Does that make sense? And well, I can take all integers here and R2 of negative. The negative numbers are not sums of 2 squares. Does that make sense?
In the first sum, it looks like we don't get any 5.
Here?
Yeah.
Here there is no 5. Absolutely. Here we only get the squares. We only get the squares, but when we multiply it by itself, now we get sums of 2 squares. And if we multiplied it by itself 2 more times, we get sums of 3 and sums of 4 squares. So you can investigate all of these things just through this one function. Now my claim, and I'm not going to substantiate this claim, is that theta is a modular form, is a kind of modular form of weight 1/2. Non-integer weight modular form. It wasn't until Shimura that people really understood what this meant 100 years after, 100 change after Jacobi. Let me just make a few observations. So observation 1 is that if I replace tau, not by tau plus 1, oh, by the way, this doesn't converge. If tau is real, I have a bunch of numbers of absolute value 1, and I'm adding up infinitely many of them, this will not converge. We can formally manipulate. I wrote this formally, but if we actually want something converging, where does tau need to live? Katie. Oh, I thought you were saying something.
In our fundamental domain.
Not necessarily in the fundamental domain, but in the upper half plane. If tau is real, none of this makes sense. I'm adding up numbers of absolute value 1. But if tau has some imaginary part, and if that imaginary part is positive, that will hit that I times I is negative. And now we have negative exponentials. And all of a sudden, we have plenty of decay in order to sum all of these things. So converges absolutely for tau in the upper half plane. We're forced to work in the upper half plane if we want this thing to converge. Okay. So if I replace tau by tau plus 1, it depends on whether I don't have an e to the 2 pi I here. I have an e to the pi I. So I should shift not by 1, but by 2 to guarantee invariance under translation by 2. Okay, if I shift tau by tau plus 2, I get a factor of 2 pi I times an integer, square of an integer. So it's obviously invariant under that. What can we say about -1 over tau? So we have translation not by 1, but by 2. What about -1 over, what can we say anything about theta of -1 over tau? In fact, we can, and in fact, it's easy to do, given everything you already know. What do you think will be a useful thing to do with a function like this? We have a sum over all the integers of something. Yes. And Poisson summation. Poisson summation of what? Remember the Gaussian? Remember our Gaussian function? F of x is e to the minus pi x squared. What's its Fourier transform? E to the minus pi x squared. If I set f sub y of x to be f of x times y, do you remember what happens to the Fourier transform? F sub y of xi? Yes, exactly. It's the original f hat shrunk by a factor of y instead of scaled by a factor of y with another factor of 1 over y coming outside. Okay, and let me remind you of the Gaussian is its own Fourier transform. If I scale a function, the Fourier transform scales by 1 over that with a factor of 1 over. And let me remind you of Poisson summation, as we already discussed. The sum of f of n is equal to a sum f hat of m. Okay, those three things mean it'll be very easy for us to work out what theta of 1 over tau is, because what is, let me write this theta function again. Theta of tau, n in z, e to the pi I n squared tau. It's not e to the minus pi n squared, but rather e to the, so this is a sum over the integers of the Gaussian f, not of n, but of n times root tau, and I want an I instead of a minus sign. So actually, if I do root tau over I, if you think about what that will do, when I square this, I'll get an n squared tau over I. That'll multiply, sorry, right here, I have a minus pi n squared tau over I, and negative over I is positive I. Now I have to make sense of this. We're taking square roots of complex numbers. We got to be careful. Which square root do we mean? Tau is in the upper half plane. So tau over I, dividing by I, multiplying by I is rotating by 90 degrees. Dividing by I is rotating back by 90 degrees. So tau divided by I is here. For the square root function, I need a branch cut. Which branch cut will I take? The standard branch cut. Okay, so I'll take the standard branch cut to define this square root. Okay, so if theta ranges from minus pi over 2 to pi over 2 for tau over I, then the square root of tau over I, the square root of tau over I has theta. In other words, the argument will be between minus pi over 4 and pi over 4. Right, square root halves the angle. So it's going to be there some. Okay. So we can perfectly well make sense of this. Poisson summation says this is the same thing as a sum over m in z of f hat of m, but f has been translated. So f hat is going to be 1 over the thing that it's been translated by or scaled by. So 1 over, so that's a square root of I over tau. And then this factor, which is f hat of m, m over y. So that's again times root I over tau. So what is that? There's this factor of root I over tau in front, and then a sum over m in z. F hat is just f, e to the minus pi x squared. And I get e to the minus pi m squared I over tau. The square root of tau I has the property in this branch cut that when you square it, you get back to tau I. What is this? So this I, let me move this I to the bottom and make that a plus sign. Sorry, actually it was okay as it was. What am I doing? I have exactly what I want. I have exactly what I want here, because this is theta of negative 1 over tau, negative 1 over tau. I'm not supposed to have the minus sign in the theta function. The theta function doesn't have the minus sign. And so we're done. So we've shown this transformation law, theta of negative 1 over tau is equal to theta of tau times this factor. The factor is tau over I, if I move it to the other side, times theta of tau. So it's tau to the 1/2. It's a modular form of weight 1/2. Not on the group SL2Z, because it's not generated by translation by 1 and inversion. It's translation by 2 and inversion. So theta is a weight 1/2. To do this properly, we have to make sense of what that means. Modular form on the group gamma, which is generated not by T and S, that would make us all of SL2Z or PSL2Z, but by T squared in S. T squared is translation not by 1, but by 2. What's a fundamental domain for that action? T squared will move the real part to, yes, the real part will get inside -1,1. What will S do? Same thing, it'll kick us outside the unit circle. So we get this fundamental domain. This is a fundamental domain for this other group, gamma. Okay, we're almost done. There's another function that is its own Fourier transform. I want to access this theta squared. So what do we know about theta squared? So theta squared of tau plus 2. Well, theta of tau plus 2 itself is theta of tau. So theta squared, of course. So if I square this equation, I get the same thing. What about if I square both sides of this equation? Theta squared of -1 over tau is equal to, I square both sides of this, tau over I times theta squared of tau. Okay, let me record that pair of operations. There's another function which is its own Fourier transform. Anybody remember? We studied it week 3. Zero function is its own Fourier transform. The cosh function is its own Fourier transform. Okay, f hat of xi is 1 over cosh xi. Hopefully you remember that. What happens if I take, let's call this function instead of theta, I don't know, psi. If I sum over all n and z, and I'll have the same thing, well, almost the same thing. I want to sum 1 over cosine of pi n tau. What does this mean? Does this converge anywhere? Let's remember what cosine is. Cosine is e to the I pi n tau plus e to the minus pi I n tau over 2. And so if the imaginary part of tau is positive, then this guy is huge and this guy is tiny. And so we have, again, massive decay. So it converges. In fact, this converges also because of this guy. If tau is in the negative half plane, it also converges. The only place it doesn't converge, at least not obviously, is if tau is real. So it converges for tau in the upper half plane. Absolutely, and so on. Okay, so we have this nice function. How can we write this as in terms of this function, f, 1 over cosh? This is f of, what's cosine? Cosine is cosh of I x. So this is f of I pi n tau. Right? I'm sorry, there's a pi here as well. Cosh of pi x is equal to cosh of pi, so I shouldn't need the pi there. And is that right? If I stick in cosh of I n pi tau, cosh I is indeed cosine. I think this is right. Okay. And what does Poisson summation say? The sum over f is equal to the sum over f hat. I've multiplied here by I tau. So I have to divide by I tau. And I get a factor of 1 over I tau in front. Okay. So, and what is this? This is 1 over I tau times a sum over f. F hat is the same thing as f. So this is a sum over m in z. F hat is 1 over cosh pi times m over I tau. The I here can be moved to the numerator with a minus sign, negative I. And cosh of I is cosine. So this whole thing is the same psi, but at negative 1 over tau. And what we've learned is that psi, and by the way, this is also invariant. Okay, I'll come back to the invariance in a second. Psi of negative 1 over tau, if I move this to the other side, is equal to IT. That I should be in the denominator. I want it to be the same as this one. Okay, fix this. It should be, I'm just going to write what should be the truth. It should be, what's that? That is what we got. I think we got it with up to a minus sign. So let's just pretend we proved this. Fix the error here. It's probably that this I belongs in the denominator. That'll fix everything, actually. Yeah. Okay. We get this transformation law for psi. And psi is also invariant under tau goes to tau plus 2. So it has the same transformation law as the theta function. And it turns out, let me, in the interest of time, so the function capital F of tau defined as psi of tau divided by theta squared of tau is automorphic, is invariant under this group action, is automorphic, which is holomorphic, which is a modular of weight 0. When I replace tau by negative 1 over tau, this factor on top and bottom cancels off. There was no factor. So it's automorphic, i.e. invariant under this group gamma. So whatever its values are on this region, that's its values on all the translates, all the gamma translates of that tile. And it's a hop, skip, and jump from there to this thing being constant. F is constant. And then when you look at what happens as you, for tau equals IT, and t going to infinity, as you go up the imaginary line, the only thing that contributes here is the term n equals 0, and the only thing that contributes here is the term n equals 0, wherever this is. The only thing that contributes here, in either case, is the term n equals 0, and in fact, that constant is 1. Implies f is 1, so theta squared of tau, which I remind you is a sum over the number of representations of n as a sum of 2 squares, is in fact equal to psi of tau, where psi is this 1 over cosine function. I'll write it in this form. A sum of 2 over cosine n pi tau. E to the pi I n tau plus e to the minus pi I n tau. You buy that? Somewhat? Okay. What's convenient at this point is, and customary to call this letter Q, let's write Q as e to the pi I tau. Then this looks more like a power series than a sum of R2 of n. Q to the n is equal to a sum n in z 2 over, this is a q to the n plus q to the minus n. Everybody see that? Now let's manipulate this a little bit. I will multiply the top and bottom by q to the n. Let's take out the term n equals 1. When n equals 1, I get 2 over 2. I'm sorry, 0. When n equals 0, I get a 2 over 2. 2 over 2 is 1. And then there's an evenness. So we get a factor of 4 instead of a 2, and then an n greater than 1. And now I have a 1 over q to the n plus 1 over q to the n plus q to the minus n. I'll multiply top and bottom by q to the n. So I get here q to the 2n plus 1. And now I'll multiply top and bottom of this by 1 minus q to the 2n. 1 minus q to the 2n. And you'll see in a second why I'm doing all these manipulations. So this whole thing is equal to 1. By the way, that's good. The number 0 is the sum of two squares in exactly one way. 0 squared plus 0 squared. That's what that 1 means. So far, we've matched one coefficient. Then there's a 4. That's good, because whatever solution x and y I have, I can change x by plus or minus, and I can change y by plus or minus. Okay? And then this sum over n greater than 1, I have a q to the n minus a q to the 3n. And the denominator here is 1 minus q to the 4n. 1 minus q to the 4n. And 1 minus q to the 4n. Notice that if tau is in the upper half plane, q has absolute value strictly less than 1, in fact. Because there's an e to the minus something. Okay, so that's why I want to write it like this. Now, 1 over 1 minus alpha, 1 over 1 minus alpha has a series expansion. It's a geometric series. This is 1 plus 4, a sum over n greater than 0. And there's a q to the n. And then this geometric series, which is a sum over, let's say, L, bigger than 0, of q to the 4nL. Right? That series is converges to this. And over here, I have a q to the 3n times a sum over L, same thing, q to the 4nL. And so if I put all of this together, 1 plus 4 times a sum over, let me call this number now m. And I want to know, how often does q to the m occur? How do I get a q to the m out of this? This is a q to the 4l plus 1. Let me combine these two. This is q to the 4l plus 1 times n. So how can q to the m, how can this contribute a q to the m? This is a sum over 4l plus 1 dividing m. I get a factor of 1 every time that happens. Every time there's a divisor of m that's 4l plus 1, it'll occur here. Once for each divisor, and that'll contribute a factor of q to the m. Over here, I get the same thing, except this is 4l plus 3. This is q to the 4l plus 3 times n. M is just an arbitrary, I'm just I'm putting the n's and the l's together to make m's. So how do I get a factor of q to the m? I get a factor of q to the m if 4l plus 1 divides m. Then that contributes once. Over here, I have a minus sign, and this is the number of divisors that are 3 mod 4 of m. These functions have names. This is called d1 of m, the number of divisors of m that are 1 mod 4. And this has a name. This is d3 of m, the number of divisors of m that are 3 mod 4. And we just proved a theorem. The number of representations, the theorem, R2 of n for n greater than 1, R2 of n is equal to 4 times d1 of m minus d3 of m. M is n. Question?
Cover like the sum of two squares theorem here, because that it's like you need
This is much more powerful. This is much more powerful. It tells you exactly how many number of representations, not only if it's representable, but how many representations. So let's try this out. Give me some n's.
Well, and this is for
This is for sum of two squares. We don't have time for a sum of four squares. When you do sum of four squares, instead of something nice like this, you'll get, what will be the weight if I raise this to the fourth power? 2. You need that forbidden Eisenstein series that we just that we didn't discuss. Instead of this Koch series, it's the forbidden Eisenstein series whose coefficients you can work out that'll give you the same kind of formula for R4 instead of R2. Okay, this is a similar computation. Just to do one example, how about 9 times 5 is 45? Okay, 45. N is 45. What are the divisors of 45? Divisors. 1, 3, 5, 9, 15, and 45. 1 times 45. Da, 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 yeah. Okay. So which of these divisors have a +1 or a -1 mod 4? This is a +1 mod 4. This is a -1 mod 4. This is 1 mod 4, 1 mod 4, -1 mod 4, 1 mod 4. Okay, so D1 is how many up arrows there are. 1, 2, 3, 4. D1 is 4. D2 is how many down arrows there are. 1, 2. D1 minus D2 is 2. So R2 of 45 is 4 times 2. I'll write it as 4 minus 2. Exactly right. That's exactly right. So these are the signs. These are the plus, minus, plus, minus. So there's essentially 2 ways. What are those 2 ways? 45, the reason this is 5 times 9. So 5 can be written as 2 squared plus 1 squared, which means this will be written as 2 times 3 squared plus 1 times 3 squared. This is 6. This is 36 plus 9 is 45. So is 9 plus 36. There's your 2 ways. And so is plus or minus of all of those. There's your 8 ways. So you get arithmetic information, theorems about number theory from studying these weird functions that have these weird transformation properties that are defined on the hyperbolic upper half plane and all kinds of good stuff. Okay.